Bad trials should not consume a full training run. Optuna Pruning watches validation results and cuts weak PyTorch experiments early. You'll learn the shape of a workflow that tests neural settings on validation feedback and cuts underperforming runs early. I'm Professor Pi, teaching AI foundations with simple Python. Training neural nets eats time and money when every lousy idea runs to completion. In practice, you only care about validation performance, not the hours spent on hopeless runs. Optuna Pruning watches validation, decides when a trial is unlikely to recover, and stops it early, so your compute goes to better experiments. Pruning simply turns one long opaque run into a series of checkpoints. Train a bit, evaluate, report a metric, and let Optuna compare that checkpoint to other trials. If a trial falls behind, Optuna stops it and frees the GPU. That saves wall time and lets you explore many more hyperparameter choices with the same budget. We'll use a tiny PyTorch regression example so the training curve is clear. The data is simple on purpose. You can see bias and underfit quickly. First, we show a baseline run, then Optuna's tuned run, and finally, how pruning trims the pointless work. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We start with a minimal PyTorch sanity check so we know the training loop behaves predictably before adding Optuna. This snippet builds a PyTorch sanity check, so the later Optuna explore exploit cycle has a reliable anchor. The cubic curve in X and Y gives trainX and validX enough shape to expose bias when model is just nn.linear. Watching Opt step through 30 passes reminds you how the gradient updates dominate behavior before tuning even starts. Because we seed with torch.manualSeed 0, anyone can replay the same gradients and the same validation curve. If you lengthen the loop, loss will keep dropping, but with diminishing returns because the model underfits cubic curvature. The printed baseline _val MSE shows the starting validation error we need to beat. Now we want to stop guessing the learning rate and let Optuna search it for us while keeping the training loop identical. This example turns that plain PyTorch loop into a proper Optuna objective, so learning rate tuning stops being guesswork. Within objective, trial.suggestFloat chooses LR in log space, keeping the atom step size reasonable for our cubic regression. The loop structure mirrors the baseline, so we can compare results apples to apples, while atom adapts per parameter. Study.optimize with n trials equals 8 is light enough for a quick refresh, yet doubling trials broadens coverage when budgets allow. The printed best MSE confirms Optuna already beats the hand-tuned baseline before pruning enters the picture. Having automated LR search, we still waste full epoch budgets on bad trials. Next, we wire a pruner to cut those early. This code tackles the wasted epoch pain directly by wiring Optuna's MedianPruner into the same PyTorch loop. Every 5 updates, we grab val from model, validX, and hand it to trial.report, so the pruner can compare against the running median. When a trial lags, trial.shouldPrune raises ot.trialPruned, freeing the GPU for a better candidate. The 5-step interval balances responsiveness and overhead. Tighter intervals preen sooner, but pay for extra validation passes. Study Optimize now runs 12 trials, because pruning slashes total training time. The printed pruned count tells you how many attempts the pruner stopped early. With some trials pruned, we must inspect study details to justify those early exits and to learn whether pruning cost us useful models. This snippet reviews the Optuna study, so you can justify those early exits with actual numbers. We separate completed trials from prune trials, then use min, t intermediate values to grab each prune trial's best checkpoint before the axe fell. Best pruned contrasts those partial results against top trial value, the lowest finished MSE. The tiny gap reminds you that pruning lost nothing meaningful. If the difference widens, relax the pruning aggressiveness or report less frequently. The printed pruned gap versus best quantifies that safety margin, so you can explain pruning decisions in interviews or reviews. Once you trust the pruner, retrain the winner from the same seed to get a stable final model and final metric. This example locks in the winning configuration by retraining with study.bestparams LR. Resetting torch.manualseed0 means final model starts from the same weight baseline as earlier trials, so you can compare metrics without stochastic drift. Final opt sticks with Atom, but now runs 80 passes, squeezing the last bit of signal from train X without waiting on underperforming trials. If you shorten the loop, validation loss stalls earlier, while longer runs barely help once we hit the optimized learning rate plateau. The printed final val MSE shows the pruned Optuna combo delivering the promised accuracy improvement over the baseline. Optuna pruning is basically an automated gatekeeper. It stops trials that fall behind based on validation checkpoints. Use it when each run is costly and you want to explore more hyperparameters faster. One caveat: prune too aggressively or report too rarely, and you can drop trials that might have recovered. Next step: try tuning the validation report interval and the pruner aggressiveness, so pruning balances early exits and safety for your real dataset. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.